Okay, let's get started. Let me have your attention. Let's get started, please. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my pleasure to introduce today's speaker, who is Dr. Charles Forsberg. He's a senior scientist in the Nuclear Science and Technologies Division of the Oak Ridge National Laboratory. Charles received his Ph.D. in nuclear engineering from MIT, and he has been at ORNL for over 25 years. Some more information about Charles. He has been a really strong friend of this department in many different ways. He's probably made more presentations to our students than any other staff member at ORNL. There might be 2 or 3 right there with you. But there's a reason for that. And that's because, as you'll see today, Charles is a very creative and productive person. It is, we're so fortunate to have people like Charles nearby where we can call on them and they can come on really short notice. And so we're very pleased he's here today. The title of his presentation is The Advanced High Temperature Reactor, which is one of his creations. Charles, you got the floor.
Today I'd like to talk about a new reactor concept. It's about 2.5 years old. We're working on a point design. If you ask a detailed question, I can assure you we don't have the answers yet. We're still very early in the design stage. In fact, we're also having the UT design class, I should say, in this department, do another design option for this particular concept at a lower power level. I'll describe where we currently stand on this new concept and why we're looking at this new reactor concept. Go on to the next slide. History, characteristics, and status of the advanced high-temperature reactor. First, it's a new reactor, emphasize that combines 3 characteristics into a single reactor. First, high temperature, 750 to 1000 C for electricity or hydrogen production. Second, passive safety, similar to the modular gas-cooled reactors. Third, large power output. As you know, modular reactors are typically 600 megawatts. We're talking about 2,400 megawatts thermal, a big reactor. Initially, it was a joint effort between Oak Ridge, Sandia National Laboratory, and the University of California. A series of studies and evaluations have been done, but we have not done a complete point design. We're in the process of developing the concept. It's a very new concept. Well, what is the advanced high-temperature reactor? What we've done is developed a new reactor by taking bits and pieces from other concepts and combining them in a new way. So the base technology is not new, but the combination of technologies is new. And we've chosen 4 technologies. First, high-temperature gas-cooled reactor fuel. Second, the molten salt coolant, transparent coolant. Third, passively safe pool-type reactor designs from the Fast Reactor program. And fourth, Brayton power cycles, such as used to produce electricity from natural gas. I'm going to show you a very simple schematic of this reactor, and then we'll go into the details. We started out with the observation that it is a pot reactor. Low pressure, big pot. Inside the reactor, we have the reactor core. It operates at atmospheric pressure. We have an intermediate heat exchange loop. It transfers heat from the main reactor to a Brayton power cycle. And we have a Brayton power cycle over here, which uses either nitrogen or helium gas. Last, we have a passive decay removal system, which I will discuss somewhat later. Conceptually, though, very simple, a pot reactor. The reality, of course, is a little more complex. The AHTR extends the high-temperature capabilities to large reactors. What this schematic shows is different reactor concepts in terms of peak temperature and electric size and output. That is megawatts electric. And here we see, of course, the light water reactor that we're very familiar with. The newest reactors on order have a capacity, or will have a output of about 1,600 megawatts electric, very large machines, but low temperature reactors. There's been a lot of work on liquid metal fast reactors. That's a high temperature reactor, a little bit higher in temperature, 400 to 500 C. Last, there's been a lot of work on modular high temperature gas cooled reactors. These are reactors typically with about 600 megawatts thermal, 300 megawatts electric. What we want to do is build a high temperature reactor that can be built in very large sizes, but with the same temperature range as a high temperature reactor. Now, fuels. First choice we have to make on a reactor is what kind of fuel we wish to use. That turns out to be very simple. There's only one type of high temperature fuel that has been demonstrated on a significant scale. So if you want to make a high temperature reactor and not have a massive fuel developments, you have one option. So that part was very easy. This shows a schematic of the fuel we're using. It is the coated particle graphite fuel that was designed for gas-cooled reactors. The key component of this fuel is the fuel particle. It contains the fuel kernel in the middle with multiple layers that act like a little pressure vessel. Each of these fuel particles is about the size of a grain of sand. Very, very, very small. The coated particle is mixed with graphite to produce a fuel compact. And the fuel compact is then put into some kind of fuel assembly. Now, it turns out you can make this particular type of fuel in many types of geometric forms. You know, you're starting with something the size of a grain of sand, so you can make it into a compact with a prismatic block, or into spheres, in which case you call it a pebble bed fuel, or into long cylindrical objects, such as was done at the Peach Bottom 1 gas-cooled reactor. So geometry options are many. But the fuel, the center of the fuel, is, of course, the particle fuel. And in our case, we've chosen to use a prismatic block, which is about 1.5 feet in diameter and about 2.5 feet high. Molten fluoride salt coolants is the coolant we've chosen. The basis for this is quite simple. Only two coolants have been demonstrated compatible with high-temperature graphite. The first is helium, high pressure, transparent. And the second option are molten fluoride salts. Note that the salt is transparent. You can see right through it. These salts typically have melting points of 400, 450 C, boiling points of about 1,400 degrees Celsius. Very high boiling point fluids. Let me provide you some background on experience of molten salts. The first observation I would make is that we have about 100 years of experience with molten salts. Molten fluoride salts are used in the production of aluminum. You take a graphite bath about the size of a football field. You fill it up with sodium aluminum fluoride, put 2 electrodes in at 1,000 megawatts, and you can make aluminum. A good example of that, of course, is the historical operations at Alcoa, where essentially they had several thousand tons of molten fluoride salt at 1,000 degrees C in graphite baths. So we have a little over a century of experience operating at 1,000 degrees C with a molten fluoride salt. That's a pretty good industrial basis. And I think we can safely say that Alcoa, over the century, has thrown everything, including probably the kitchen sink, either accidentally or deliberately into their bath. So we have a lot of experience in what you might call off-normal operations. We also have a limited amount of experience as a reactor coolant. In the 1950s and the 1960s at Oak Ridge National Laboratory, they developed something called the molten salt reactor. This reactor had a molten salt coolant, but they put the uranium in the coolant. It was dissolved in the coolant. Now, what we're talking about is something different. We have a clean coolant, but this particular reactor provided a lot of experience in understanding molten salt properties and how to pump them and how to use them on a large scale. Now, why would we want to use molten salts? What's the function of molten salts? Why is it a good coolant compared to helium or other gases? I'd like to go through 3 slides, of which all have essentially the same story. Liquids are better than gases if you want to transfer heat. And we'll talk about it in 3 different contexts. First, let's take a look at molten salts in terms of the capability to transport heat. And what we're asking here is the number of 1-meter diameter pipes needed to transport 1,000 megawatts of heat with a 100 C rise in temperature. And we show this for various reactor coolants. Here we show it for water. It takes about 3/4 of a pipe. For sodium, you need 2 pipes. For helium, you need 12.5 pipes. For molten salt, you need a half pipe. Now this is very important because the size of your pumps, the valves, the piping, the major components in a reactor are dependent upon the ability to transport heat. The better the fluid is at transporting the heat, the smaller the equipment, and hence there's a strong incentive to have the right properties of the coolant. The next slide shows that liquids remove heat more effectively than gases. Now, this is not a real surprising occurrence. Any of you who've gone swimming on a summer day have probably noticed that when you jump from the air into the water, you cool off much more rapidly. And that's a consequence that liquids are, of course, better coolants than gases. This is a much more complicated slide that shows the same story in the context of a reactor, but it's the same message. What this shows here is the temperature versus the distance across a fuel element from the coolant channel, this is the coolant channel, to the hottest point in the fuel. And what we show in the red line is what happens if we have helium cooling. With the same power levels, we have molten salt cooling, we have this particular line here, and you'll notice that it's about 75 degrees C less rise in temperature by using a good coolant, a liquid, rather than a poor coolant, a gas. Now, we're talking about molten salts, but this would apply to any liquid coolant versus any gas coolant. It's not really specific to the coolant. The last observation I'd like to make is that for any coolant exit temperature, the average temperature of delivered heat will be higher with a liquid coolant than a gas coolant. Let me explain this curve. Vertical axis has temperature. The horizontal axis has the coolant reactor inlet temperature and the coolant reactor outlet temperature. Now let's take a look at gas-cooled reactors first. Now let's take a look at the British advanced gas reactor. Carbon dioxide cooled reactor. Exit temperature about 650 C, inlet temperature a little over 400 C. There's about a 350 degrees temperature drop in temperature rise across the reactor. If we look at the GTMHR gas-cooled, helium-cooled reactor, same thing, 350 degrees C temperature difference between the inlet of the core and the outlet of the core. Now let's take a look at a liquid-cooled reactor. Let's look at the old standard run-of-the-mill pressurized water reactor. 20, 30, 40 degrees C temperature drop across the core depending upon who the manufacturer was, whether it was combustion or Westinghouse. Pick your vendor. Some have 20 degrees, some have 30, some have 40, but that's a minor engineering detail. Well, why is this important? Let's say we want to have output of a reactor at 1,000 degrees C. If we have a liquid coolant at 1,000 degrees C, like our molten salt reactor, the average temperature of the heat dumped from the reactor to the power cycle will be about 950 C. So we get almost all of the heat delivered at high temperatures. If we have a gas-cooled reactor with the same exact exit temperature, we find the average temperature of the delivered heat is a little over 800 degrees C. So for the same exit temperatures, the gas-cooled reactor delivers its heat at a much lower temperature to the power cycle, and that means lower efficiency. What counts is the average temperature of the delivered heat. In short, liquids are better coolants than gases. Any of you had it? I don't know what the heat transfer course in this department is, but I think probably your professors have probably mentioned this more than once, that liquids are better cooled than gases. As you can tell, I like to work on simple engineering concepts rather than complicated concepts. Facility design. Well, we've got the coolant and we've got the fuel. How do we put a facility together again? Well, what we're talking about is a low-pressure, high-temperature machine. Have we built low temperature, low pressure, high temperature reactors in the past? Well, the answer to that question is yes. We have designed and built a number of liquid metal fast breeder reactors. This happens to use sodium. This happens to be the design of the General Electric S-Prism sodium-cooled fast reactor. But the key thing is this is a low-pressure, high-temperature machine. We wish to build a low-temperature, little bit higher low-pressure, a little bit higher temperature reactor, so we can use the same basic type facility design. So we're just going to borrow facility designs from the fast reactor people, change the metallurgy a little. I have to do that, make a few other changes, but use the same basic plant design concepts because we have the same constraints. It's a liquid. It runs at high temperature. The particular reactor we decided to borrow, facility design to borrow, was the S-Prism of General Electric. The reactor core is in a silo underground. The building is mounted on a seismic pad. Remember, General Electric's headquarters is in San Jose, that's California, so they have a lot of concern about seismic. The cores are here. They have an intermediate heat exchanger to a secondary loop with a turbine hull to the left side. On the right side, of course, we have spent fuel storage. Now, we took the General Electric design and we made a couple of modifications, and as a consequence of those modifications, we can put a 2,400 megawatt AHTR nuclear island, the same size plant as a 1,000 megawatt sodium cooled reactor. And I'll explain how we did that. The first important difference is we took, in their case, they stored spent fuel in the vessel, and we moved the spent fuel out of the vessel and moved the heat exchangers out of the vessel. The second thing we did is we decided that our reactor would use the same size vessel as the S-Prism. We have a lower power density fuel, so we said if you've got a vessel this size at such a power density, how much power can you put in? Is 2,400 megawatts. The third is we have similar equipment size. As I showed in an earlier curve, molten salts are about 4 times better than sodium for moving heat around. Translated, the equipment size shrinks by a factor of 4, except we're working a little bit higher power level. But with a better coolant, we can put more reactor, more facility in the same plant. We changed the heat decay cooling system, which I will describe later, and we went to much higher temperatures, which means much higher efficiency of the reactor. Let me briefly describe the decay heat emergency cooling system for the S-Prism reactor, which is the same that we're using. We have a reactor core. It's in a low-pressure vessel with a guard vessel. To remove decay heat, we have air that circulates around the vessel and back out. Now, the way this system works is that we have a guard vessel, a regular reactor vessel, and a guard vessel here. And the heat transfer across this zone is a function of temperature. It depends upon radiation cooling. And radiation cooling goes as the 4th power of the temperature. Now, we're willing to go to a little bit higher temperature because we're going to use a Hastelloy vessel rather than a stainless steel vessel. And because of that, we're willing to go to higher temperature vessels. Because of the large change in heat rejection as a function of temperature, if we raise the temperature of the vessel 100 C, we can remove the decay heat from a 2,400 megawatt reactor that was previously used to remove the decay heat for a 1,000 megawatt reactor at a somewhat lower temperature. Basic laws of heat transfer. I'm going to briefly describe 3 passive decay heat cooling systems here that are very similar to give you a better feel of passive decay heat cooling systems. And I'm first going to describe the similarities and the differences. In each of these reactors, we have a silo that is cooled, air-cooled silo of some type, common feature. In the first reactor, we show the MHTGR, the Modular High-Temperature Gas-Cooled Reactor, that I'm sure many of you heard about. In fact, I think it was discussed last week, if I remember correctly. Now, the HTGR has a wonderful fuel. We'd, of course, say that because we're using the same fuel. But if you look at it, the hot point in the reactor is in the middle of the reactor. And to get the heat out, decay heat out, you have to move the heat from the center of the vessel to the vessel wall by conduction through 15 feet of graphite. Well, graphite's an okay conductor, but not that good. As a consequence, it takes almost 1,000 C in temperature to move that heat, decay heat, this distance to the wall, And then, of course, you have to move it from the wall through the cooling jacket to the outer environment. But the large temperature difference to make the system work means that you're limited to the power level of about 600 megawatts electric. Induction heat limited system. Let's take a look at S-Prism. S-Prism is a sodium-cooled reactor. That means the entire vessel is filled with sodium. The temperature from the hottest to the coldest point of this vessel in an emergency is about 30 degrees Celsius. So we have very efficient heat transfer from the reactor core to the vessel wall. No 1,000 degrees C, only 30 degrees C. Consequence? We can have a passive decay heat cooling system for a 1,000 megawatt reactor. Remember, all these reactor vessels are the same size. Last, advanced high temperature reactor. Same type of system. You have a liquid cooling system for efficient heat transfer, but we're willing to go to higher temperatures for the vessel because we're willing to use a Hastelloy vessel. Consequence, we can have a reactor of 2,000 megawatts with the same general type of decay cooling system because we're changing from conduction heat transfer to convective heat transfer to very high temperature operations. Change of phenomena changes how we do decay removal. Reactor core design. We're using a reactor core that looks very much like a gas-cooled reactor. I understand last week Sid Ball described gas-cooled reactors. If you drained out well, you actually wouldn't need to drain out the molten salt because you can see through it. If you looked at this reactor core, you'd say, looks just like an HTGR core. Now, if you look really closely, you discover the cooling channels are a little bit smaller, and there's some minor changes in dimension, but that's nothing you would notice on a TV screen. You have to get the detailed engineering drawings. So a very similar reactor core, a little bit larger in size. The reactor vessel, of course, is in a silo with the reactor core at the bottom and a large area above for molten salt. The molten salt provides us a lot of additional decay, the ability to absorb decay heat in a variety of emergencies, and thus provides a safety function. To briefly mention electricity and energy conversion. This is a liquid-cooled reactor that operates at a high temperature. This allows us to do some things that cannot be done in other types of reactor systems. In particular, we can use something called a multi-heat Brayton cycle, which was probably given one paragraph in your heat transfer course, maybe two. Theoretical interest in the past, currently a lot more interest because we're running with a liquid at a high temperature. We first thought that nobody had looked at these. It turns out somebody in the 50s had looked at it, and sure enough, in some of the classical heat transfer books, there was about 2 paragraphs that described the concept. We have the reactor, intermediate heat exchanger, and the Brayton power cycle. Now, what we're talking about is a power cycle like a gas turbine power cycle. What's different in this multi-reheat cycle is that the high-pressure helium, or nitrogen, goes through one turbine and is then reheated back up to its full temperature, goes through a second turbine, reheated to its full temperature, goes through a third turbine, and then goes through the recuperators and back through all the compressor chain. The key item is that we reheat multiple times. We provide most of the heat to the power cycle at very close to its peak temperature. And when you provide most of the heat to a power cycle close to its peak temperature, you're much closer to a Carnot cycle. And a Carnot cycle, of course, describes the most efficient cycle for the conversion of heat into electricity. So we're going to be using a Brayton Carnot cycle, a multi-reheat cycle. A couple of items to be noted about Brayton cycles, particularly large Brayton cycles. The Brayton cycles have the wonderful characteristic that they're a lot smaller than steam turbines. What this shows is a scale comparison of a 1,300 megawatt electric boiling water reactor versus a 1,300 megawatt advanced high temperature reactor. This is the AVWR power hall. This is the advanced high temperature reactor power conversion unit to scale. This is a lot smaller. Why is that possible? There are 2 reasons. We think of a steam cycle as an efficient cycle, but it has a major problem. If you go into a steam turbine hall, you find out that most of the building is filled with these low-pressure turbines that are operating at 1/10 of an atmosphere. They're big. They're monstrous. I think many of you have probably been in power plants. I mean, they take up most of the space. In a internal Brayton cycle, our lowest pressure is something like 7 atmospheres, 70 times higher pressure, which dramatically shrinks the equipment. So we avoid all of that very expensive apparatus and size. The other thing is we have higher efficiency, and higher efficiency means fewer cooling towers. In short, there are a lot of incentives to go to these Brayton high-pressure cycles to shrink equipment. Brief note on economics. Large reactors have the potential of lower capital costs. Our economic goal is to drive the cost below $1,000 a kilowatt, and we plan to do that by 3 strategies. The first we want is economics of scale. 1,200 megawatts electric is a big reactor. The second, we want high efficiency. Minimizes cooling towers, water handling systems, a variety of other systems. And third, we want to go to lower power systems, such as the Brayton cycles that have intrinsically lower costs than traditional steam cycles with a very low pressure. Our current cost estimates are actually below $1,000 a kilowatt, though, of course, we're very early in the design of this reactor, so there is a very large uncertainty in our cost estimates. But we think we have the right strategy. Big size, high efficiency, and advanced power conversion units. Now, of course, as a consequence, this can only be used in certain markets. It can only be used in markets in the United States, Central United States, Europe, Japan, and China. It cannot be used in developing markets or in edges of the grid where you can't tolerate a large grid failure. This is a machine for the middle of a large industrial state. It's not a machine for Japanese islands like Guam that are isolated from everything else, Indonesia, West Australia, South Africa, or even parts of Europe that are on the far sides or the far edges of the grid. This is a big machine for the middle of a national grid, not the edges of a national grid. Research and development. Well, there's a lot of overlap from a lot of other reactors. That's because we took every key technology from another reactor, without exception. The R&D requirements for the molten salt cooled AHTR and the helium cooled HTR are much in common. Well, same fuel, essentially the same high temperature materials, electrical production cycles, and hydrogen production cycles. In short, we're borrowing technology. We have to integrate it in a new way, but we're borrowing technology from everybody else that's we're doing work on research. And that's very important if you have a new reactor concept. If you have a new reactor concept where everything is new, the development cost of time is just incredible. So we're in the borrowing game, big time. Now, some conclusions. The first, it has a number of attractive features. We're going for high temperature, and that's for efficient power production and hydrogen. Second, we think it'll have good economics for large utility grids. I mean, this is a large utility grid machine. It's not for people on the edge of the grid. It's not for small countries. It's not for places like Guam or South Africa or even northern Canada. It's just not suitable for that. And of course, the economics depend on large power output, compact design, and high efficiency. We're going for passive safety. It's both important in terms of public acceptance, but we think it's also important in terms of cost. Last, there are a couple of challenges. In fact, there's a surplus of challenges because it's a new concept. We're working on a point design. We're looking at several molten salts. We haven't decided which one exactly to use. There are many variants of the decay heat cooling systems, and there are many variants of the core design. This is very new. As a consequence, we don't have the answers that you can find in the textbooks. The answers will be in the textbooks maybe in 20 years, but they're not there yet. One of the things you begin to realize if you start working on an advanced reactor concept is just how much work it takes to get a point design. People do not appreciate when they pick up a textbook. They go hundreds of thousands of hours to work out a design, a facility design, or another type of design of another component in a reactor. It takes an incredible amount of effort. We've discovered that one of the big advantages we have is that we are borrowing technology. But even if you borrow the technology, it takes a lot of work to make it all fit together. There are other challenges, high temperature, and of course the high melting point of the salt. Now the chemical industry does use molten salts and heat transfer loops to about 600-700 C. We're probably going to operate higher than this. Molten salts, freezing points, depending upon the salt, 300, 350 C. So there's a set of separate engineering issues associated with keeping the molten salt molten. Chemical, it's standard procedure in the chemical industry, but it's a very new experience for the nuclear industry because we're not used to dealing with molten salts and the special requirements of it. I think I'll stop at this point and turn the class back to Professor Dodds.
Okay, we now have time for questions and comments.
They're bashful, just like church.
Right.
What are your main three criticisms, and how have you handled them?
Most of our criticisms are we're not there yet, which is absolutely true. Did I bring it? Let me see. Back at Bluegrass. When you start talking about advanced design, one has to separate the difference between where you are and where you want to be. And what we show here is where we are, where we think we are, in terms of where we want to be. This is the temperature of the reactor output. This is the hydrogen electrical output. Where we want to be is out here somewhere. In terms of existing technical foundation, we have materials of construction that will go to about 750 C, and our decay heat cooling system using very conservative calculations will allow us to build an 800 megawatt electric reactor. That's where we are. Where we want to be to move the economics is out here. And so one has to recognize that there is a significant difference between where we are, that is, we know we can build it at 750 C, we know that the decay heat cooling system will take out the heat for 800 megawatts electric, and where we want to be. And one must always keep in mind existing foundation and where you want to head in terms of R&D. And we've got a fair distance there. And usually most of the discussions we're having is not designing in this space, but how to get from here to there. The other one, of course, is this issue of freezing points. If you've got somebody with a chemical industry background, they say, what's the issue? If you have somebody with a nuclear background, don't understand that. That's sort of a cultural, industrial culture, which industrial culture you came out of.
Loss of coolant isn't one of your...
No. If we have a loss of coolant, we'll flood the silo and have decay heat going out through the silo. That's why it's in a silo. So we can't have a loss of coolant accident.
One of the early, I guess, the EMSR experiments out at Oak Ridge, the touted advantage of that cycle was one could have online refueling. Does this concept involve that kind of thinking?
No. This is a solid fuel reactor you shut down for refueling, just like all other solid fuel reactors. Well, I stand corrected. There's something called a pebble bed reactor that has online refueling of pebbles. But this is prismatic fuel for a variety of neutronics reasons, and that means you have a standard outage for refueling.
What form is the uranium in for?
It's a uranium oxide in these little microspheres that are coated with pyrolytic carbon and silicon carbide.
Have you considered going to carbide fuel or nitride fuel to increase the operating temperature some?
Our strategy right now is to borrow any proven technology as far as we can because we have enough other uncertainties. So we are not trying to push fuel development. Our answer is we'll take what you have and borrow it, and when we get everything else working, then we'll come back and look at an improved fuel. But the strategy when you're looking at a new reactor concept is to forget about major improvements in the base technologies unless you absolutely require them. Let me give you another example. We're looking at an option of a helium Brayton cycle or a nitrogen Brayton cycle. And our initial thought is we're going to use a nitrogen Brayton cycle. Not quite as efficient, but there's a very good reason to use it. If you go out and take a look at a jet engine at the airport and you ask, what kind of turbine do they have in there? The answer is, they have a nitrogen turbine. Now, it's true, there's a little oxygen and air, and they add a little kerosene, and they heat up the nitrogen. But if you ask how that turbine was designed to run on nitrogen because 80% of air is nitrogen. Okay, well, nitrogen turbines are not as good as helium, but you can buy them off the shelf. And so for our particular concept, our initial concept, is that we will use a nitrogen Brayton cycle for the very simple reason that there are two vendors whose bottom line is, if you want a nitrogen Brayton cycle, send us an RFP and we'll deliver. If you want a helium Brayton cycle, a little more efficient, send us $500 million in 10 years and then we'll deliver. So in our case, we are not trying to push any technology that we don't absolutely have to push to make the concept work. And fuels, our bottom line is we're not going to change the fuel. Long term, second generation, third generation, yes, but initial term, no. Conservative where we can be conservative.
Larry, a couple of questions. One is there any appreciable constraints on helium as a coolant, just as a resource? And the other one would be, is there any significant or concern about production of carbon-14 with the graphite fuel?
The first question on helium is we probably have no helium shortage as long as we burn lots of natural gas. And the reason why is most of our helium is extracted as a minor impurity from natural gas. And in particular, when people convert natural gas to liquefied natural gas, and they liquefy the natural gas, they often find there's a little helium mixed with the natural gas that shows up in these liquefaction plants. As long as you've got big natural gas industry, you have helium. Now, once you start running out of natural gas, that's an entirely different situation. Then you may find that helium becomes a very, very expensive commodity. So it's tied to the natural gas industry. And I'm afraid I forgot your second question.
On carbon-14 production with the graphite core.
We're going to be just like the HTGR.
I know, but I've read different things about that. One, it is a significant issue if you had hundreds of these things, and others that it's not. So have you done the calculation?
It's going to go to the repository. The graphite has to go to the repository.
Yeah, the carbon-14, though. The carbon-14 production, and then...
yeah, but it's tied up with the graphite.
Right, but then there are limits on carbon-14 releases from the repositories as well.
Yes, but you can design the repository to keep the leak below those limits. That's fairly straightforward. But the catch is you do have to send all the graphite, including the shielding blocks and the supports, will ultimately all have to go to the repository. That's the unfortunate part about graphite reactors. It'll ultimately end up in a power reactor in the repository.
Well, weren't they considering at one point on gas reactors 20, 30 years ago of incinerating graphite?
Yes, I was involved in that. And I was the one who took a first-generation look at what we do with the carbon dioxide when you incinerate it during a reprocessing operation. And the answer was you mix it with calcium hydroxide and make calcium carbonate, put that in the mine. But the bottom line is, given current regulations, you will have to go to the repository. Carbon-14 is one of those things, if you build one reactor, you don't care. If you build 1,000 reactors, you simply can't let it go to the environment. It's a question of how many reactors and how much releases. But it's not, what is, I forgot what half-life, 5,000 years, something like that. It's not that hard to deal with in a repository where everything else lives a great deal longer than carbon-14. It's an expense. There's no way around that.
Larry?
Charles, when do you plan on finishing or completing, I'll say, the point design?
I would hope within the next 18 months we'll have a reasonable point design. We're working away bit by bit, piece by piece. Depends on funding.
That was my second question.
We're beginning to get funding, but there's a lot of confusion in the country on where we're going with reactors. The good news is we're getting a lot of attention and a lot of vendor interest. So both vendor and DOE interest in this particular reactor concept, primarily because on paper the economics look a great deal better than anything else that's out there. We've had a couple of people who looked at this, and their bottom line was, if you can get the technology to work, the economics are great.
Have you gotten any support from DOE yet?
Yes.
Any significant support?
Well, it's dramatically improved in the last couple of months.
Okay, sure.
It's evolving.
David?
I know this isn't your technology, but those microspheres are interesting because you have this detailed geometric thing on something so small. Technology and fuel cost and all of that. Can we make those things?
People have made them, but I'm the wrong one to ask. And you can make them on a production scale. It's a sort of a solar cell process. Put it in a fluidized bed, you put multiple coats on it. It's a pretty high-tech fuel. It's going to be a more expensive fuel than LWR fuel, which is really quite cheap.
We do have experience with pebble bed reactors about 20, 30 years ago in Germany, and they used the same concept. And the fuel aspect of that was very successful.
Both Germany and Japan.
Yes.
And China are manufacturing.
That's right.
And we're setting up a fuel line at ORNL.
That's right.
For research level.
I don't think the question is not whether you can make the fuel, it depends on how hard you push the fuel. I think you can make the fuel. The issue is working the economics and the engineering to drive down the cost when you get into a large-scale production, and keeping the quality at the same time. It's a quality cost in a high-volume production issue. The Germans and the Japanese have made some wonderful fuels. The way I would describe the U.S. history over the last 20 years or last 30 years is some days we made good fuel, and some days we made bad fuel. And if you're going to run a power reactor, it's got to be every day is good fuel day. And that's the part we haven't gotten to yet. It's a manufacturing issue. It's a big manufacturing issue.
Okay, do we have, right?
I wanted to mention one other idea from GE that would really be good in this design, and that would be licensing by demonstration. You want to go at that low temperature, all that white is,
Yes.
and then just convince the NRC that you're going to gradually raise that temperature and go right up to where you want to be.
That would be a prudent idea.
That would be and your module is small enough. You could do it at a test site,
Oh, yes.
like, Argonne's
Yeah,
reactor.
we're not proposing a 2,400 megawatt first generation plant. We're probably talking about a fairly small reactor for a first proof of principle concept to work out the details.
But you're going to have to hopscotch
Yes. Work up on temperature.
3 designs to get to where you want to be.
Oh, yes.
Start with the
I'd
size
agree.
you want, and gradually show by demonstration that you meet all the safety.
Oh, yes, yes. You want to work up the curve in temperature. No big jumps.
Isn't the student design project a smaller version
Yes,
of this?
yes. That's one of the advantages of the student design project. University of Tennessee is the second group of people to look at this concept. And because nobody knows what a smaller reactor looks like, we're going to have them tell us. You've got to understand how relatively small the effort is. BWRs and PWRs evolved. Many people looking at many different designs to get where they are today. We are not there yet. We're looking at one little design space, and UT is looking at another little design space, and it's going to take a while with different people looking at different design spaces and temperature and size to understand what the real issues are and what the options are on this machine, and that remains to be determined. Yes, we're looking at a smaller reactor, which is much more likely to be the near-term type of thing that might actually be built.
Right, I should give credit to the leadership for that project. That's Dr. Fred Minott and about a dozen students that he has. And they're working diligently on that small reactor concept today. Well,
Is there any U.S. vendor involved in this design?
Not currently. We're having discussions with a U.S. vendor. Having discussions with about two vendors right now.
Larry?
Were you going to try to get this in the Gen 4 category, or have you tried?
This was developed during the Gen 4 process.
Did they revisit?
What happened is the definition is that it has changed perspectives. That needs a little bit of explanation. In the Gen 4 concept, one of the areas that was defined as an advanced reactor concept was a very high temperature reactor. And this concept sort of evolved during the Gen 4 process and is now considered one of the Gen 4, a type of very high temperature reactor. At the current time, in terms of the U.S. context, there are 4 reactors that are being examined as very high temperature reactors. One, of course, is the General Atomics prismatic helium-cooled 600 megawatt reactor. The second is the Westinghouse pebble bed helium-cooled modular reactor. Third is the Framatome prismatic helium-cooled indirect cycle reactor. And the fourth one is this reactor. So we're one of the 4 that are put into this category, this class called very high temperature reactor.
Isn't there a molten salt reactor
Yes,
in
yes.
Gen 4?
That's a molten salt fueled.
Yeah.
Now, the French were also involved in Gen 4, and they looked at these approved Gen 4 lists, and they said, well, the VHTR, that's a type of molten salt reactor. So in their categorization of Gen 4 reactors, this is under the category of molten salt reactor rather than very high temperature reactor because there's a molten salt coolant. So the good news is, depending on which country you are, we're on the list. It's just that we're in box A, B, C, or D, depending upon which country you're in. This sort of evolved, it actually evolved in the process. I mentioned our 2 partners, Per Peterson of Berkeley and Paul Picard of Sandia. What really happened is the 3 of us were on the same panel and went out to lunch too many times, and this sort of grew out of those discussions. Strange way things actually, in the real world, actually develop.
Actually, that's the way things do develop.
Oh.
Over the coffee machine and at lunch. When we go to these meetings, we get these ideas. End result of those three people getting together several times.
Many, many times.
Okay, do we have any other questions or comments? If not, let me remind everyone that we do have refreshments downstairs, and Dr. Forsberg will be down there to answer more questions and enjoy the refreshments with us. But before we adjourn, let's express our appreciation to him for his presentation.
Very nice electronic.
I don't know.